Hello class, I'm glad that you could join me for our first virtual lesson. So right now you're going to find the paper that I gave you that says Unit 7, Lesson 1 up at the top. So some of you will see that this already has writing on it, that's fine. Some of you will see that this paper is blank, that's also fine. So these first three problems are our warm-up problems. I would like you guys to try this on your own first before you see how it's done on the screen. Let's take a look at question 1. For all of these problems, we are going to be factoring and solving. So for this first problem, I want to look at what 3x squared minus 6x has in common. What do these two terms have in common? So I notice that 3 is divisible by 3 and negative 6 is divisible by 3. So something that they both have is a 3. Alright, let's take a look at what else they have in common. I can see that the first term has an x and the second term has an x. So since both of them have an x, we can write that out front. So always, out in front of our parentheses, we're going to have what the two terms have in common. In this case, a 3 and an x. And then inside of our parentheses, we're going to have what's left over when we take that away. So if I have 3x squared and I remove the 3 and the x, what's left over? I'll just have 1x left over. Right, let's look at this negative 6x. If I take the negative 6 and take away the 3, so negative 6 divided by 3, I am left with negative 2. And this x goes away, so we're just left with the minus 2. Alright, let's set that equal to 0. So now we have these two different terms that we want to set equal to 0. I'm going to take this, 3x, and make it equal 0. Then I'm also going to take the x minus 2 and make that equal 0. Alright, I'm going to have two separate equations set equal to 0. Then all we have to do is solve for x. So over here, in order to get x by itself, I'm going to have to get rid of the 3. That can be done by dividing both sides by 3. The 3's cancel. So we have x equals 0 divided by 3. If we use our calculator, we see 0 divided by 3 is 0. So that's one of our answers. X equals 0. Let's look over here. In order to get x by itself here, I want to get rid of this negative 2. So I can add 2 to both sides of the equal sign. That makes this go away. So we just have x is equal to 2. That is our second answer. Alright, let's move on to something else. Question 2. We want to factor this. So whenever we see a factoring problem like this, x squared plus some number times x plus a number by itself, we want to take a look at the last number. In this case, that's 9. So I want to make a list of everything that multiplies to get 9. 1 times 9, 3 times 3. And then we want to add to get 6. So I know 3 plus 3 is 6. So these are the two numbers we're going to use, 3 and 3. We're going to build our answer here. When we're factoring, we always want to write our answer like this. Our answer is going to be placed inside of these two parentheses. And we're going to use the numbers we found earlier. So we're going to say x plus 3, x plus 3. Right, now that I have these two things, I want to set them equal to 0. So I have x plus 3 equals 0. And I could do that again. I could write another thing that says x plus 3 equals 0 for this one. But that's a little bit unnecessary because we're going to get the same exact answer. So I think we can just leave that out. Right, now we want to solve for x. So I want to subtract the 3 from both sides of the equal sign. This goes away, so we have x equals negative 3. That's our answer. Let's try number 3. Alright, this one looks a tiny bit different from number 2, because you'll notice there's a number in front of the x. And this isn't an x squared, it's an x to the third. So we're going to have to want to factor out some things here. Let's look at what all 3 of these terms have in common. 2 is divisible by 2. 10 is divisible by 2. And 12 is divisible by 2. So all 3 of these terms can be divided by 2. So I want to write that on the outside here. So like always, whatever is on the outside is what the 3 terms have in common, and what's on the inside is what's left over. Let's look at what else they have in common. So I have an x here, an x here, and an x here. I can only take out one x because there's only one x available here in the last term. So we're going to write that out. We're going to factor out that x because we can take an x out from all 3 of those terms. So let's write what's left over here. If I have 2x to the third, I factor out a 2 and I factor out an x. What's left over? I have an x squared. Because I have 3 x's and I take away 2 of them, or I take away 1 of them, and I'm just left with 2 x's. That can be written as x squared. Right, over here with the 10x squared, if I have a 10 and I factor out a 2, that's the same as dividing. So I'll be left with a 5. And if I have 2 x's here and I take away 1x, I'll just have 1x, so 5x. Lastly, we have 12x, factor out a 2, take away an x, we'll just be left with 6. Alright, now just like the first problem, we're going to set each of these equal to 0. So I'm going to take the 2x, make it equal 0. Then I want to take this side, x squared plus 5x plus 6, make that equal 0. Alright, let's look over here. To get x by itself, I want to divide by 2, so x equals 0. And over here, I'm going to have to factor this. I'm going to have to take an extra step here. So I want to look at this last number, and I want to make a list of everything that multiplies to 6. 1 times 6, 2 times 3, and we want to add to get that middle number 5. Well, we see 2 plus 3 is 5. So these are the 2 factors we're going to use. So whenever we factor, our answer is written in 2 parentheses. So x plus 2, x plus 3. Now we take these 2 things and make them equal 0. So x plus 2 equals 0, x plus 3 equals 0. We solve for x. We have x equals negative 2 and x equals negative 3. So we ended up having 3 different answers on this problem. Right, on the rest of the page, you'll see the vocabulary we're going to see throughout this unit. Let's move on from that, and let's look at our definition for a polynomial. So this whole unit, we're going to be working with polynomials. Let's define that. So, a polynomial is an expression that can have constants, variables, and exponents. So let's give an example of a constant. So think to yourself, see if you can remember what a constant is. A A constant is just going to be any number without a variable. So 8 is a constant. -2 is a constant. Any number without a variable, and it's usually at the very end of our polynomial. All right, a variable. What are some examples of variables? We could have x or y. Those are the two common ones that we see. And lastly, we have our exponents. So that's when our variable is raised to a certain power. So like x to the 4th power or y squared. It's when our variables are raised to an exponent. All right, let's take a look at some characteristics of a polynomial. It's easiest to talk about what a polynomial cannot be. So, a polynomial cannot have negative exponents. Let's see what that would look like. An example would be like x to the -2 power. Anytime we have a negative exponent, we just say, oh, that's not a polynomial. We're not going to see anything like that. What else? We cannot have division of a variable. So for example, that would be something like 3 over x. If we have a variable at the bottom of a fraction, that means this is not a polynomial. So we're not going to see that. We don't want that. What else can't we have? We cannot have any radicals. So an example of that, the square root of x. We're not going to see that because our polynomial cannot have that. All right, let's take a look at some examples of polynomials. So something like a constant as simple as 17. This could be a polynomial. Or something like 8x. That would be a polynomial. Something else, we might have 3x squared plus 2. That's a perfectly good example of a polynomial. Something like this, we might have x to the 7th power plus x to the 5th power plus 3. That's a good example of a polynomial. So all 4 of these can all be polynomials. Let's take a look at something that is not a polynomial. What about 12x to the -3rd power? Why isn't this a polynomial? Think to yourself for a second. Well, it violates one of our rules. We can't have negative exponents. So that certainly is not a polynomial. Let's see here. What about 6 square root of y? So because of that square root, that disqualifies it from being a polynomial. Something else. What about 2 over x? That's not going to work. And just one more, like x to the -2 plus 3x plus 5. So this looks like a polynomial, but because of this negative here, it's not one. Okay. So I'd like you to practice this. We have 4 different examples here, and I'd like you to figure out whether or not they are polynomials. So look at them, see if there's anything in our list of things that will disqualify it from being a polynomial, and write down your answer. So over here, on this first one, we see that we have some division here. So while you might be tempted to say, oh, that's not a polynomial because there's division, I want you to be careful on that because this is division of just numbers. It's only when you have division of a variable that it's not going to work. So let's say that that was like 1 over x. that means it's not a polynomial. But this is 1 over 8x. The x is not being divided here. It's not at the bottom of the fraction. So this is perfectly okay. There's nothing wrong with that. So we can say, yes, it's a polynomial. Let's look over here. One big thing we can see right away is that -2. So we want to say no, it's not a polynomial, and we want to say why. That's because it has that negative exponent. Right, over here, our x variable is at the bottom of a fraction. That's a big no-no here, so we say no, it's because we have division of a variable. Last one, we have 12. So 12, it's just a constant, as we saw right here. That's a perfectly good example of a polynomial. So we could say, yeah, this is a polynomial. There's nothing wrong with it here. Doesn't have any negative exponents or square roots or division of variables. Right, let's move on. Let's look at classifying our polynomials. So mathematicians love to classify things. We have different names for all of our polynomials. But the first thing I want to look at is what a term is. So right here, we have 4 different terms in this polynomial. So terms are always separated by a plus or a minus. So you'll notice here, there's a minus sign, there's a plus sign, there's another minus sign. Each of my terms is separated by a plus or a minus. So let's look over here. We do not have any plus or minus signs. If that is the case, then we say that this only has one term. It's just this one block here. We call it as one item, it's one term. Over here, we do see a minus sign. It's separating the 5x and the 1. So we have 2 terms here. There's 2 separate things being separated by that minus sign. Next up over here, we have a plus sign and a minus sign. So that gives us 3 terms because we have 3 different things being separated by a plus or a minus. So 3 terms. Now we have different names for these. Think about a prefix that means 1. A prefix for that would be mono, like monotone. If somebody's speaking in a monotone voice, they just speak at one note the entire time. We call this a monomial, where mono means 1. Right, 2 terms. Let's think of a prefix that means 2. So bi, I think of the word bicycle having 2 wheels, or bilingual, 2 languages. So we can write this as a binomial, where bi means 2. And 3 terms. Our prefix for that would be tri. So this would be a trinomial. You can think of a tricycle, it has 3 wheels, or a triangle, 3 sides. Alright, let's start filling in some notes here. So, the degree of a polynomial with only one variable is the largest exponent of that variable. Right, so the degree of a polynomial with only one variable is the largest exponent of that variable. Let's take a look at an example here. I want to look at all of the exponents in this example. So I can see that I have an exponent of 3. That exponent of 3 is my largest exponent. So we say the degree is 3. Whatever this largest exponent is, that is our degree. So I'd like you guys to try that following example. Look at which exponent is the largest, and that will tell you what the degree is. Alright, so let's take a look at all of our exponents. We have a 2, a 3, and a 7. Obviously 7 is the largest out of all of those, so we say that our degree is 7. Alright, let's take a look at writing these in standard form. So the standard form for writing polynomials is to put them with the term with the highest degree first, and continue down until the term with the lowest degree is last. Alright, so in this example, let's find our highest degree. So we have an exponent of 2, an exponent of 3, and 6. Well, let's first start by saying that our degree is 6, because that's the largest exponent here. But now we want to put it in order. We want to put it in standard form. So I'm starting with that highest exponent, x to the 6th. Because that's the highest exponent, it goes first. Okay, what's the next highest? X to the 3rd. So I'm going to write that next, 4x to the 3rd. That goes next in my polynomial. Then I have an exponent of 2, so I want to write that 3x squared next. And the last one is our constant at the end, -7. So this is standard form for a polynomial. It always goes from our exponent being the greatest and dropping down to the least, and we're usually going to end in a constant here. Right? For an exercise, I'd like you to organize these examples from earlier. We want to write them. Well, this one's already in standard form, but you can try this one. So take a moment, pause the video, give it a shot. Alright, we know that our degree is 7, so I'm going to write that highest degree first. That's that -3x to the 7th term. Then we have x to the 3rd, so I'm going to write the 4x to the 3rd. We have x squared, so we have the 7x squared. We have the 5x, and we have the 2. So I would say that this is the standard form for that polynomial. Alright, next let's take a look at roots. So when I ask for roots, that means the same thing as the solutions of the polynomial. We can find these roots or solutions when we set everything equal to 0, just like we were doing in the warm-up. So let's do this example. Our degree of this polynomial is 6, because that's our highest exponent. And we want to go ahead and solve it. We want to factor it. So let's look at what these 3 terms have in common. So this 4 is divisible by 4, so is this one. And -24 is also divisible by 4. So let's write that out. I know that all 3 of those terms have a 4 in common, so I'm going to write that out in the front. Alright, let's take a look at this. We have 6 x's here, 5 x's here, and 4 x's. So at the most, we can take out 4 x's. So I'm going to factor out that x to the 4th, because they all have that in common. Alright, Now that I have this, I have 4x to the 6th. So that's like writing x 6 different times. And if I take away the 4 and take away 4 x's, what am I left with? I just have an x squared. So 4x to the 6th, factor out 4x to the 4th, you're just left with 2 x's, x squared. All right, 4x to the 5th. We take away the 4, we take away 4 x's, we're just left with 1 x here. And then negative 24x to the 4th, we divide that by 4, we get negative 6. We had 4 x's here, and we took away 4 of them, so we have none left. We're just going to be left with that negative 6. Now what we want to do is set this equal to 0. So our 4x to the 4th power is going to equal 0. And then x squared plus x minus 6 is going to equal 0. Right, over here, we can divide both sides by 4. So we have x is equal to just 0. And then over on this side, we want to factor. So we want to look at the last number. That's negative 6. I want to see what multiplies to get negative 6. So negative 1 times 6, negative 2 times 3. And let's look at the number we're trying to solve for here. Any time that we have a variable without a number in front, we can just say that it's 1. So I'm trying to add up to 1. And I know that negative 2 plus 3 equals 1. So these are the two factors that I want to use. So just like always, we're going to factor using our two parentheses. We have x minus 2 and x plus 3. Then we can take each of those and set them equal to 0. So x minus 2 equals 0 and x plus 3 equals 0. We're going to solve to get x equals positive 2 and x equals negative 3. So we have three answers here. X is 0, x is 2, x is negative 3. Okay, let's look at a different example. We want to go ahead and solve this the same way. So this is very similar to our warm-up. We want to identify what all three terms have in common. So 3 can be divided by 3, 18 can be divided by 3, and 27 can be divided by 3. So since all three terms are divisible by 3, we're going to factor out that 3. It goes out in front of our parentheses. What else can we take out? We can take out 3x's from all of those terms. So we're going to take out x to the 3rd. All right, now we are going to write what is left over. If I have 3x to the 5th and I take away 3, and then I take away 3 x's, I will only have 2 x's left over. So x squared, because that's 3 times 5 x's, and we end up eliminating the 3, and we end up eliminating 3 x's. We just have 2 left over. Right, 18x to the 4th. We want to take the 18 divided by 3. We're left with 6. So we have a 6, and then we have 4 x's, take away 3, we just have 1 x left over. Lastly, we have 27x to the 3rd, so 27 divided by 3, that gets us 7. Oh, no. That gets us 9. So then we have 9, and we have 3 x's, we take away 3 of them, we have none left over. So this is our answer here. Okay, let's separate this out. So we have 3x to the 3rd equals 0. Then we have x squared plus 6x plus 9 equals 0. So we want to factor this. We're going to end up with an answer with 2 parentheses. So we're paying attention to that last number. 9. What multiplies to get to 9? We have 1 times 9, or 3 times 3. Just like in our warm-up, we see that 3 plus 3 is 6, which is that middle number that we were trying to get. So we can write our answer, x plus 3, x plus 3. So like we saw in our warm-up, I could write x plus 3 equals 0 2 different times, but we get the same answer both times, so it's kind of silly. So x equals negative 3. I can write it again. Oh, and over here, we divide by 3, we get x to the third equals 0, x equals 0. All right. So sometimes we're going to get an answer more than once, just like we got here. We have x equals negative 3 twice. So we have a double root at x equals negative 3. A double root, that means we have the same root twice. Let's look at a triple root. So we had the same root 3 times. So over here we notice x to the third equals 0. So 3 different times x equals 0. We could have written it out like this. That's kind of silly to do. We just noticed that that exponent of 3 means we got the answer 0 3 different times. So we have a triple root at x equals 0. So we have a word for this. This is called multiplicity. So the multiplicity of a root is the number of times that the value of x is a factor for the function. So when a root has an even multiplicity, the graph of the function touches the x-axis but does not cross it. So like a parabola. Let's imagine an xy axis here. We know that parabolas touch the x-axis and don't cross it. So when we have an even multiplicity, wherever our root is, we can say that it bounces. Our function, our graph, touches the x-axis, but then it bounces right back up. It doesn't cross it. All right, when a root has odd multiplicity, so odd multiplicity greater than 1, the graph bends as it crosses the x-axis, like a cubic function. So our cubic function, that would look something like this. So here, this would be an odd multiplicity, and the graph bends. It crosses through. All right, so let's visualize this. I like seeing things visually. So an even multiplicity, we're going to bounce off of the x-axis. So we're going to touch the x-axis at one point, and we're going to look like this. Our graph is going to look like that. Odd multiplicity, when the multiplicity is greater than 1, it's going to look like a cubic function. So the graph is going to bend a little bit when it crosses the x-axis. And when the multiplicity is exactly 1, that's a different case. We're just going to go straight through the axis without any bending. So let's look at that in terms of this example up here. We had a triple root. So that means we had a multiplicity of 3. 3 is an odd number. So because it's odd, it's going to bend. It's going to look like that cubic function. And then we have a double root. Double means 2, so that means we have a multiplicity of 2. 2 is an even number, so that means our graph is going to bounce here. So the graph will bend here, and it will bounce here at x equals negative 3. All right, we can also determine the multiplicity of a graph just by looking at its graph. So right here, I want us to take a look at the point negative 3, 0. We know that this has to be an even root. It has a multiplicity of 2 because it's bouncing here. The graph touches the x-axis, but then bounces away from it again. So that means it's even. And let's look at 0. The graph bends there, so it looks a bit wavy when it crosses the x-axis. So that means we have odd multiplicity. We have a triple root. But sometimes we can't say for sure what the multiplicity is from a graph. The surefire way to know is by factoring. So like we did up here. I can totally determine the multiplicity of a polynomial by factoring it. So here I know that I had a multiplicity of 2 because I had the same exact answer twice, and a multiplicity of 3 because I had the same exact answer 3 different times. All right, we can try another example. So here, our polynomial is already factored for us. We've already gone through the step of factoring it, and now we just want to set it equal to 0. So we have 3 of the same thing being set equal to 0. So I could write that out 3 times, but that's kind of silly. So let's just solve it once. So we're going to have x is equal to negative 2 3 different times. All right, let's take a look at this. My degree is going to be 3. So we kind of have to think about what this polynomial would have looked like before we factored it. We're going to have, we're going to have 1, 2, 3 x's. So I don't know exactly what my polynomial looks like right now because I haven't multiplied it through, but it would have started with x to the 3rd because I have 3 different x's here. So that is going to be my degree. The highest exponent I'm going to have is 3 for this problem. My number of solutions, I just get that x is equal to negative 2. That's one solution here. We can identify the root as being x is equal to negative 2. That is my solution, because remember, solution means the same thing as root. So we had one of those at x equals negative 2. Then we want the multiplicity. So we saw x equals negative 2 3 different times. So my multiplicity here is 3. Because remember, I could have solved 3 of these. I could have set all 3 of them equal to 0. But that was a little bit unnecessary. So we just say that we have a multiplicity of 3. All right, this one, let's take a look at our degree. So it's already factored for us again, but we want to think back to what did this polynomial look like before it was factored? So we have x to the 3rd, that's 3 x's. We add another x, and then we have x squared, so there's 2 x's here. So we have x to the 3rd and another x and an x squared. So let's count that up. That gets us 6 because we have 3 plus 1 plus 2. That's 6 So our polynomial would have looked like x to the 6th before we factored it. Okay, let's solve this to find our number of solutions. So we're going to take each part individually and set it equal to 0. So 2x to the 3rd equals 0. We can divide both sides by 2. We get x to the 3rd equals 0. So we have x equals 0 3 different times. And that's because of this exponent of 3. Alright, let's take a look at this. X plus 1 equals 0. We can subtract 1 from both sides, so we get x equals negative 1. Right, we only got that answer one time. And then next up, we have x minus 6 equals 0. And based on the exponent outside of the parentheses, we saw this answer 2 times. Because think about it. X minus 6 squared means the same exact thing as x minus 6 times x minus 6. So I could have set both of those equal to 0 and gotten this same answer twice. So let's look at our number of solutions. I have 1, 2, 3 solutions. What are my roots? Well, one of my roots is x equals 0, the other one is x equals negative 1, and the last one is x equals 6. Then I want the multiplicity of each root. So we had x equals 0 3 different times, so my multiplicity for that is 3. We only saw this answer once, so that multiplicity is 1. And we saw x equals 6 2 times, so that multiplicity is 2. Let's look at what the different types of graphs will look like. So if something has a degree of 1, a simple example of that would be y is equal to x. That's just going to look like a straight line. Another way that could look is like y equals 3x plus 2. Our degree is 1 because the highest exponent is 1. So then something for the degree of 2, that would look like y is equal to x squared. That's our simplest one. Or it could look like y is equal to 2x squared plus 6 or something. So our degree is 2 because the highest exponent is 2. So that's always going to look like a parabola. Next up, we might have a degree of 3. So y is equal to x to the 3rd. This is our cubic function, and our cubic functions always have this funny, like, squiggly S shape. A degree of 4, that would be like y is equal to x to the 4th power, and it's always going to have this kind of funny W shape. And lastly, we have a degree of 5. Oops, so y is equal to x to the 5th, and that one's just kind of crazy looking, kind of like an M for a W. Alright, we're going to use all of the information that we learned to start sketching the graph of these functions. So that's the key word here, is sketch. That means that it doesn't have to be perfect, but it does have to be based on everything that we learned. So what will help us out here is listing everything that we can about the function. Let's look at the degree first. So we have 1x here, then we have an x squared, then we have an x to the 3rd. So we have 1x, then we have 2 x's, then we have 3 x's. If we add up all those x's together, we get 6. So if we were to unfactor this, if we were to put this back into the standard form of the polynomial, our polynomial would start with an x to the 6th term. And then it would have all this other stuff at the end, but we won't know that until we multiply it. So we say that our degree here is 6. All right, let's take a look at the orientation. So basically, that means what is like the shape of the graph. So because we have a degree of 6, that is an even degree. We can look back at these different degrees that we saw here. So notice that a degree of 1, that's an odd number. Our graph ends up pointing in 2 different directions. When we have a degree of 2, that's an even number. Our graph on both ends up going up. They both go relatively in the same up direction. Whereas here, one goes up, one goes down, and over here, both of them are at least going up. All right, 3 is an odd number, so one end ends up going up, the other end ends up going down. 4 is an even number, so we see the same result here. Both of the ends of the graph end up going up. So what we can deduce from all these different examples is that if we have an odd degree, either end of the graph is going to, one end is going to go up, the other end is going to go down. If we have an even degree, both ends of the graph will end up going up. So at the end of the day, I can say that no matter what happens in between, both of the ends of the graph are going to go up. All right, we want to see how many solutions there are. So for my solutions here, let's see. We can set x plus 2 equal to 0, x minus 3 equal to 0, and we'll have that result 2 times. And then we can have x plus 5 equals 0, and we'll see that happen 3 times. So here we have x equals negative 2, x equals positive 3, and x equals negative 5. So we have 3 different answers, negative 2, 3, and negative 5. And those are where our roots are at. So negative 2, 3, and 5, negative 5. All right, what kind of curves does it have? So we see right here on this first example, we have a multiplicity of 1 because we only saw this answer once. If I have my x equals negative 2, we have a multiplicity of 1. We know that that's just going to look like a straight line. Because let's go back to what our different multiplicities look like. If our multiplicity is exactly 1, it's going to look like just a straight line. X equals 3. We have a multiplicity of 2 here because we have that exponent of 2. We saw that answer 2 times. That means we have a multiplicity of 2. When we have a multiplicity of 2, that's when our graph will bounce. So it's going to resemble that shape. And then lastly, we have x is equal to negative 5. We ended up seeing this answer 3 times because it had an exponent of 3. That's a multiplicity of 3. 3 is odd. And if it's odd, so if we have an odd multiplicity that's greater than 1, 3 is greater than 1, it's going to look like that funny bendy shape. So we're going to have that bendy shape at x equals negative 5. So we're going to use all this information to help us graph this. So let's actually go to the roots. Let's go to x is equal to negative 2. That happens right here. We know for sure that the graph is just going to pass straight through in a straight line. At x is equal to 3, we know that the graph is going to bounce there. It's going to look like a U shape. And at x is equal to negative 5, we're going to have that bendy S kind of shape. All right, another thing that we know is that our graph needs to point up at both ends. So no matter what happens in between, our graph is going to go up at one end and up at the other end. So we can just roughly sketch what this is going to look like. So this is going to have a weird bendy shape because of what we saw here. And now at the red part, it's just going to pass straight through without any bending. And then at the blue part, it's going to have a bounce. So it's going to touch the blue part and bounce up again, and the graph is going to keep going straight up. Alright, I don't want us to worry about the y-intercept right now. That's something we can focus on later. I would just like us to get good at doing rough sketches of what this graph is going to look like. So, to reiterate, we have a weird bendy shape at x equals -5, so we showed that here. Our graph makes a straight line at x is equal to -2, so we go straight through it, and here we kind of bend. And at x equals 3, we bounce, so we have a U shape here. At either end, we're going to go straight up based on what we saw earlier because we have an even degree. Right. The best way to get better at this is to practice, so let's practice another one. I'd encourage you to try this one on your own and then check back with how I do it on the video. So, first thing we want to look at, what is our degree? So we have x here with an exponent of 2. So that means I have 2 x's here. Then I have an x with an exponent of 3. That's 3 x's. So in total there are 5 x's. That means my degree is 5. Let's look back at what a degree of 5 would give us. 5 is an odd number. So because we have an odd degree of 5, that means one end is going to go up, the other end is going to go down. So we can make a note of that for the orientation of this graph. One end is going to go down, something's going to happen in between, and the other end is going to go up. So no matter what happens in this middle section, we just know it's going to end, well, it's going to start with the graph going down, and it's going to end with the graph going up. All right, let's look at our solutions. So I want to take each of these and set them equal to 0. So x minus 2 equals 0. And we see that happen 2 different times. Then we have x plus 3 equals 0. And that happens 3 different times. We get that same answer 3 times. So we have the answer x equals 2 twice. And we have the answer x equals -3 3 different times. So we know that we have 2 solutions here. We have 2 intercepts. The graph is going to touch the x-axis at 2 places. Right, let's look at those roots. One is x equals 2. The other one is x equals -3. I don't want to look at our y-intercept right now. We can ignore it. And then we want to look at what kinds of curves it has. So at x equals 2, that has a multiplicity of 2 because we saw that answer twice. We had an exponent of 2. So when we have a multiplicity of 2, that means that our graph is going to bounce. And we know that by looking back over here. 2 is an even number, so it's going to look like a U shape. Alright, for x is equal to -3, we saw that answer 3 different times. So that's a multiplicity of 3. An odd multiplicity is going to get us a bendy shape, like an S shape. So let's draw that on our graph. I'm going to put a point down at x is equal to 2 and x is equal to negative 3. I know eventually the graph has to go down at the first end and the graph has to go up at the other end. Now we want to figure out what's happening in between. So at x equals negative 3, right here, we know it has to have that bend. It has to have that S shape. So it's going to pass through while it bends. And then when x is equal to 2, it's going to bounce. Just like we predicted here. So we said our graph was going to bounce at 2. That's what happened. And we said that our graph was going to bend at negative 3. Make that little S shape. So this is just a rough estimate, a sketch of what our graph is going to look like. That's our lesson for today. Make sure that on Google Classroom, on this assignment, you hit that blue button that says turn it in so that I can make a note that you've actually done it. I would also like it if you take a picture of all the pages in the packet and upload it to Google Classroom under the assignment. If you're having trouble with anything on Google Classroom, feel free to email me, text me. I'd be happy to help you.